Okay, so far we have seen the fundamentals of conduction and convection. Third mode of heat transfer is radiation. Now at the end of this session, you will be able to understand what is radiation heat transfer and what is the fundamental law of radiation and what is emissivity and how to estimate heat transfer by radiation. You can see in this figure the heat received by the earth from the sun by means of radiation. Radiation is an electromagnetic phenomena where the heat transfer takes place through electromagnetic waves. These waves carry the energy in the form of photons, and all bodies, by virtue of their high temperature greater than 0 Kelvin, continuously emit energy in all possible directions, and that mode of heat transfer is called radiation. The electromagnetic radiation from the sun heats the earth. This is what we have seen in this figure. The higher the temperature of an object, the more thermal radiation it gives off. In the process of radiation, ideal body considered is black body. A perfect black body is a surface that reflects nothing and emits pure thermal radiation. For example, the white hot filament of a bulb is a black body because all light from the filament is in thermal radiation and almost none of it is reflected from other sources. So the fundamental thing which we should know in the radiation is whenever a body or a surface temperature is greater than 0 Kelvin, please note it is not 0 degrees centigrade, 0 Kelvin. That body, by virtue of its temperature, emits energy in all possible directions in the form of electromagnetic waves, and that mode of transfer is called radiation. The radiation is governed by Stefan-Boltzmann law. The Stefan-Boltzmann law says that the total power emitted by a black body is directly proportional to its surface area and also directly proportional to fourth power of its absolute temperature. Q is directly proportional to area and fourth power of its absolute temperature. So if you remove the proportionality, you have to introduce a constant sigma, which is known as Stefan-Boltzmann's constant. Hence we can write the equation Q is equal to sigma A T to the power 4. This Q equal to sigma A T to the power 4 as defined by Stefan-Boltzmann law is applicable only for a black body. A black body, you know, is the one which absorbs everything into it. And later on in the chapter on radiation, we will come to know that good absorbers are good emitters. So black body is a perfect emitter. So when compared to other bodies, the emitting energy coming from a black body at the same temperature will be highest, maximum. So Q is directly proportional to the area of emission and the fourth power of its absolute temperature. The sigma value is very low, 5.67 into 10 power minus 8 watt per meter square Kelvin to the power 4. Q is in watts, area meter square, temperature should be in Kelvin, and hence the unit of sigma is watt per meter square Kelvin power 4. Because the value of sigma is very low, in the order of 10 power minus 8, unless the body temperature is very high, we do not experience the radiation heat. Only objects at high temperature, the emitting energy our body can feel. For example, if you sit before an ordinary light, you don't feel any radiation, but if you sit before a 500 watt floodlight, after some time you can feel the radiant energy coming from the bulb filament and falling on your body. As I said, radiation is a phenomena which occurs by virtue of its temperature. It is not related to the temperature difference between one object to the other object. It is the property of a single body itself by virtue of its temperature being greater than 0 Kelvin. We all know that at 0 Kelvin the molecular motion ceases. When the temperature is greater than 0 Kelvin, there will be a molecular motion, and then electrons will change their orbital levels. In the process of their change from one orbital level to the other orbital level, they emit energy or they release energy, and that energy which comes out from the body due to the motion of molecules by virtue of its temperature being greater than 0 Kelvin is known as radiation. And it is given by the Stephen-Boltzmann law. Q is equal to sigma AT to the power 4. The black body is an ideal body which emits maximum amount of energy, and all real bodies emits energy less than that of a black body, because a black body is a perfect absorber as well as a perfect emitter. So with reference to the emitting capacity of a black body, we compare the emitting capacity of other real bodies. Hence, the emissivity epsilon of a body is defined as the ratio of energy emitted by a real body to that of energy emitted by that of a black body. So emissivity epsilon is equal to E by EB. E suffix B means black body, or Q by QB. We know Q suffix B, the emitting energy by a black body, is sigma AT to the power 4. Therefore, the heat transfer by radiation from a real body Q is equal to epsilon into QB. Epsilon into sigma AT to the power 4. So this is the energy emitted by a body at temperature T. In the surroundings, we have a number of bodies, and all the bodies' temperature is greater than 0 Kelvin. So each body, by virtue of its temperature greater than 0 Kelvin, continuously emit energy into the environment at the rate of epsilon sigma A to the power 4. For example, my body emits energy, and the other objects also emit energy in the form of radiation. The energy emitted by all other bodies, a fraction of it will come and fall on my body, and the energy emitted by my body will go and fall on the other objects. So there is a continuous interaction of radiant heat energy among the bodies present in environment. If you consider only two, that is a body and environment, only one body in the environment at temperature Ts, Since this Ts is greater than 0 Kelvin, the body emits an energy equal to epsilon sigma A Ts to the power 4. The environment is also at a temperature T alpha, free stream temperature or environment temperature, which is also greater than 0 Kelvin. Hence, this environment also emits energy at the rate of sigma A T alpha to the power 4. Hence, the net rate of energy heat transfer by radiation is equal to Q is equal to epsilon sigma A Ts to the power 4 minus T alpha to the power 4. How did we get this relation? The details of it we will see more in the chapter on radiation. So now fundamentally the radiation heat transfer is governed by the law, Stefan-Boltzmann law, which says that the amount of energy emitted by a black body is directly proportional to its area and fourth power of its absolute temperature. All real bodies cannot emit energy as much as by a black body. Therefore, we define emissivity epsilon for a real body equal to amount of energy emitted by that real body to that of amount of energy emitted by a black body. So we say Q for a real body is epsilon sigma A T to the power 4. Whenever a body is kept in surroundings at T alpha, the net radiant heat energy between the body and environment is Q equal to epsilon sigma A Ts to the power 4 minus T alpha to the power 4. Now let us have a look what we have covered so far in the fundamentals of conduction, convection and radiation. Heat transfer is nothing but part of thermodynamics where the time factor is taken into account. That is why in thermodynamics we measure heat in joules, whereas in heat transfer we measure it in watts, joule per second. The fundamental modes of heat transfer are conduction, convection and radiation. Conduction is dominant in solids, convection in liquids and gases, and radiation in vacuum. Radiation of course is effective only at high temperature. The conduction is governed by Fourier law of conduction, Q equal to minus Ka dt by dx. The convection is governed by Newton's law of cooling, equal to HA delta T. The radiation is governed by Stefan-Boltzmann law, Q is equal to sigma A T to the power 4, and these are the three basic laws explaining the three different modes of heat transfer. Remember, it's very important, in conduction the area to be considered is normal to the direction of heat flow, whereas in convection and radiation the area, though we are giving the same notation A, but the area to be considered is exposed surface area to the environment. Many times students do mistake here only in considering area as surface area or cross-sectional area, otherwise, etc. So don't fall in the trap. Conduction is with reference to the area normal to the direction of heat flow, whereas in convection and radiation the area which is going to be in contact with the surrounding medium, that is nothing but surface area. In conduction we have introduced the constant K called thermal conductivity, and in convection we have introduced the constant H, convective heat transfer coefficient. In radiation we have introduced a constant sigma, Stefan-Boltzmann constant. Thermal conductivity K is the property of material and is highest for pure metals, followed by alloys, non-metals, crystalline and amorphous substances, finally liquids, and least in case of gases, which we have seen it in the first lesson. Thermal conductivity of pure metals decreases with increase in temperature, whereas the thermal conductivity for alloys and non-metals increases with increase in temperature. And in radiation, while using the equation Q equal to sigma A T to the power 4 or epsilon sigma A Ts to the power 4 minus T alpha to the power 4, the temperature of the body must be taken in Kelvin, whereas in convection and conduction it is not essential, because these two are governed by temperature difference. Whether you take the temperature in Kelvin or degree Celsius, the temperature difference remains same, hence there is no criteria there. So this is the first part which dealt with the fundamentals of conduction, convection and radiation. Let us have a look at the model problems. Calculate the rate of heat transfer through a steel plate of 0.5 meters width and 0.4 meters height and 5 mm thick, having thermal conductivity 40 watts per meter Kelvin, when its phases are maintained at 100 degrees and 30 degrees centigrade respectively. I am assuming that the thermal conductivity of the plate is uniform and thermal conductivity is not a function of temperature and it is purely one-dimensional heat conduction, and it is completely under steady state. The data given is width of the plate is 0.5, height of the plate 0.4 meters, the thickness denoted by L is 5 mm, 5 into 10 power minus 3 meters, one face is at 100, the other face is at 30. You are asked to determine the rate of heat transfer through the plate, which is nothing but by means of conduction. So relevant equation used for solving this problem is Fourier's equation, Q equal to minus Ka dt by dx. dt is temperature difference, dx thickness in the direction of heat flow, that is L, minus Ka delta T by L. And as I said, A is the area normal to the direction of heat flow. This is direction of heat flow, and normal to this direction is this face area, which is equal to 0.5 into 0.4, 2 meters square. Substitute the parameters in the equation. Q equal to minus Ka delta T by L, Q equal to minus K, thermal conductivity given as 40 watts per meter Kelvin, area 0.5 into 0.4, which is 2 meters square, delta T, final minus initial temperature, 30 minus 100, thickness in the direction of heat flow, 5 into 10 power minus 3, hence Q is equal to 1.12 watts. Because this delta T always heat flows from high temperature to low temperature. When I consider delta T, it becomes obviously negative, because final temperature minus initial temperature. To make this positive only, Fourier has introduced the negative sign, as we have seen in the fundamentals of conduction. Rate of heat flux is directly proportional to negative temperature gradient, that minus sign. Now you understand why the minus sign is given here, to make this positive value. And you can see that the temperature variation along the length of the, along the thickness of the plate is linear. This we will prove it at a later stage. Temperature linearly varies from 100 to 30. Another problem on convection. A hot steel plate, again say thermal conductivity 40 watt per meter Kelvin, of 5 mm thick, this is shown here, having its face area 0.5 into 0.3 meter square, is maintained at 200. The surface temperature is maintained at 200 degrees centigrade. If this is exposed to a current of air at 20 degrees centigrade, that is air is flowing, imagine, at 20 degrees centigrade, having convective heat transfer coefficient 10 watt per meter square Kelvin, determine the heat carried by the air due to convection from the surface. Given data is thermal conductivity 40 watt per meter Kelvin, thickness 5 mm, length 0.5 meters, width 0.3, surface temperature of the plate, this surface temperature 200, the fluid flowing air temperature 20 degrees, the convective transfer coefficient H is 10 watt per meter square Kelvin. The relevant equation is Newton's law, convective transfer Q equal to HA delta T, where A is the surface area. So here the surface area exposed to the motion of air or the molecules of air is 0.5 into 0.3, that is 0.15 meter square, and Q is equal to H 10.515 Ts minus T alpha 200 minus 20, which is equal to 270 watts. The thickness and thermal conductivity given in this problem is superfluous data. Convection is a surface phenomena and nothing to do with the thickness or property of the material. It only depends on the properties of the fluid. Even this is not a steel plate, imagine, even if it is a copper plate at 200 degrees centigrade, convective transfer coefficient is 10, air is at 20, area is 0.5 into 0.3, Q remains same. So nothing to do with the property of the plate material here, and nothing to do with the thickness because it is a surface phenomena. Hope you will understand. Then third problem on radiation. Consider a steel ball of density, is again on convection. Steel ball of density 7,800 kg per meter cube and specific heat, etc. is placed in atmosphere. Calculate the initial rate of cooling in degrees centigrade per second. Assume the convective transfer coefficient is 15. Neglect the heat loss by radiation. See here, the steel ball is at 300 degrees centigrade, kept in environment at 30. So from the surface of the ball, the heat is lost to the environment by means of convection. So as the ball starts losing heat energy to the environment by means of convection, the total amount of energy stored in the ball goes on decreases. In thermodynamics, we have learned the holding capacity of a ball with respect to the temperature rise is mCp delta T. Now that mCp delta T is in joules, whereas the rate of heat lost to the environment is in watts. So to create a dimensional homogeneity, we consider the rate of heat energy lost by the ball, not the total energy possessed by the ball, but at what rate it is losing its energy is given by mc delta T by dt, time. The small t represents time and capital T represents temperature. mc dt by d small t equal to HA delta T, convective heat transfer. Look at this energy balancing equation, very important. The rate of heat energy lost by the ball. Ball is losing heat energy, and that energy enters into the environment by means of convection. So therefore, as per the law of conservation of energy, the energy lost by the ball is equal to the energy that enters into the environment by means of convection. So mc dt by d small t equal to HAS Ts minus T alpha. Mass is density into volume, and surface area of the sphere is 4 pi r square. By substituting different parameters in this, you will get the change in temperature with respect to time, d capital T by d small t, as 0.33 degrees centigrade per second. Note that this rate of cooling is only in the initial condition, the starting. As time progresses, the Ts varies, therefore the rate of change in temperature with respect to time also changes. So this value 0.33 degrees centigrade per second is valid only in the initial condition. Therefore calculate the initial rate of cooling at that time when the body temperature is at 300 degrees. What is the rate of cooling? That is around 0.33 degrees per second. Now this is another problem which illustrates the combined mode of conduction, convection and radiation. All the three are involved in this. Imagine a steel plate at 400 degrees centigrade having thermal conductivity 35 watts per meter Kelvin, whose top surface is maintained at 400 degrees centigrade. Surroundings are at 25 degrees centigrade, having convective heat transfer coefficient of 20 watts per meter square Kelvin. Calculate the temperature at the bottom of the plate, this point. Top of the plate is given as 400. What is the temperature at this point? Assume heat loss by radiation from the surface is 500 watts. It's a very interesting problem. Suppose the plate is kept on a induction stove. The moment you switch on that stove, heat starts entering into the plate from the bottom surface and reaches the top surface by means of conduction. So the heat starts flowing from bottom to the top through the plate within the solid by means of conduction. The amount of energy that reaches the surface by means of conduction now can enter into the environment by two modes. One is by means of convection and the other is by means of radiation. So the energy balancing equation is the rate of heat entered into the plate and reaching the surface by means of conduction should be equal to the amount of heat loss from the surface into the environment by means of radiation plus convection. So Q conduction is equal to Q radiation plus Q convection. The formula for convective transfer according to Newton's law, HA delta T, you know H, you know the surface area, and we know the delta T, you can calculate it as 3750 watts. And the radiation heat loss from the surface is given as 500 watts. So the total heat loss from the surface is 3750 plus 500, 4250 watts. See, though the plate is losing 4250 watts of total heat energy from its surface, still the surface temperature is maintained at 400 means continuously the surface should reach that energy from the bottom. So the Q conduction should be equal to the Q conduction, it should be equal to the Q radiation and the Q convection, which is equal to 4250 watts. So Q conduction 4250 equal to K 35 area normal to the direction of heat flow, bottom cross sectional area 1 into 0.5, and T inside surface and T outside, T in minus 400 by thickness of the plate 0.05 meters. It is given as 0.05 meters. So which will give you the inside plate surface temperature is 412.14 degrees centigrade. You can now the bottom surface is at 412, top surface is at 400. Heat transfer takes place from bottom to top by means of conduction. Whatever amount of heat is received by the surface by means of conduction enters to the environment by means of convection and radiation together. And because the energy gain is equal to energy loss, the surface temperature is maintained at 400. It's an important problem having all the three modes of heat transfer in it. Another problem on radiation. Consider a solar flat plate collector. The top glass is maintained at 40 degrees centigrade and its surface area is 2 meters square. The environment is at 30 degrees centigrade. Determine the amount of heat transfer by radiation from its surface. Consider the emissivity of the surface is 0.85. So as we have seen earlier, the environment emits energy, the surface also emits energy because of the temperatures being greater than 0 Kelvin. So the net radiant energy is epsilon sigma A Ts to the power 4 minus T alpha to the power 4, where epsilon is given as emissivity 0.85, sigma 5.67 in 10 power minus 8, area, exposed area is 2 meters square, Ts and T alpha should be in Kelvin 313 to the power 4 minus 303 to the power 4, 112.68 watts. This is the net radiant heat exchange between glass surface and environment. This amounts to loss of heat from the surface. So some model problems also we have obtained which illustrates how to apply the Fourier law of conduction, Newton's law of cooling, and then Stefan-Boltzmann law. This is the fundamental part of conduction, convection and radiation, and in detail the next sessions we will see conduction, different types, different mode, and convection and radiation. I request the listeners to go through these review questions and try to prepare answers. This session we are not going to discuss the answers for these questions. Maybe after a few sessions, at the end of the lecture, you will find answers for these questions also. In the meantime, please try to solve and try to prepare answers for these questions. The question 1, what is the driving force for heat transfer? and what is the driving force for electrical current? Each other. The third question, consider two houses that are identical except that the walls are built using bricks in one house and using wood in the other. If the brick walls are twice in thickness when compared to wood, which house do you think will be more energy efficient? It's a conduction based problem. Fourth question, consider heat loss through walls of a house on a winter night. Walls are identical except that one of them has a tightly fit glass window and other one is completely wall. Through which wall will the house lose more heat? Again, conduction based. Next, fifth one. Can a medium involve both conduction and convection simultaneously? Both conduction and radiation simultaneously? Both convection and radiation simultaneously? Yes or no? If yes, give examples for each case. Next, sixth question. Why do we characterize the heat conduction ability of insulators in terms of their apparent thermal conductivity instead of the ordinary thermal conductivity? Very interesting question. Answer for this is with reference to the poor thermal conductivity of air. Think in those directions, you will get the answer. Next, seventh. Consider an alloy of two metals whose thermal conductivities are K1 and K2. Will the thermal conductivity of the alloy be less than K1 or greater than K2 or between K1 and K2? So try to get the answers for these questions. Anyhow, I will be presenting the answers for these questions in the coming sessions. Further suggested reading, I prefer in the same sequence The Heat and Mass Transfer, a Practical Approach by Jonas A. Sengel, the McGraw-Hill Company book. Principles of Heat Transfer by Frank Reith, Cengage Learning. And then Introduction to Heat Transfer by Incrobera and Dewitt, John Wiley and Sons. And of course the last one is written by me only, Heat Transfer, a Conceptual Approach by Professor P.K. Sharma and K.